In the last lecture, we studied the interaction between an electric dipole and an electric field. We found that when we place an electric dipole in an electric field, then there is a couple which acts on the dipole. The dipole rotates either this way or that way, so that ultimately it comes in the direction of the electric field. That is, the dipole moment is parallel to the electric field. That is the position of least potential energy, and therefore, the position of stable equilibrium. In this lecture, we introduce another concept, electric flux, and we study Gauss theorem, which is so important in electrostatics. What is electric flux? Let us use in ordinary English language. Flux means the rate at which a liquid or a gas enters or leaves a surface. For example, if there is a surface, if something is leaving this surface, the rate at which this liquid or gas leaves this surface is called its flux. In the case of electric field, it means the number of lines of force going through this surface. Remember that the surface area is a vector quantity. We will make use of this fact. Now, suppose we have a surface denoted by sigma, which has a surface area S. This surface is placed normal to the lines of force. This means that the normal to the surface is parallel to the electric field. Then we say that the flux going through this surface is the area of this surface into the magnitude of the electric field, that is E times S. Now, suppose this surface is slightly at an angle to the electric field, that is, the normal to the surface makes an angle theta with the electric field. Then the surface area of this surface normal to the lines of force or normal to the electric field is S cos theta, and therefore, the flux through this surface is now E S cos theta or E dot S. Now, take another example. We have a surface which is curved, and on this curved surface we choose a small elemental area d s. The normal to this makes an angle theta with the electric field through this elemental area. Then the flux through this elemental area d s is E dot d s, and the flux through the entire surface is simply the integral of E dot d s. And if the surface is closed, then the integral E dot d s is replaced by the integral over the entire surface. That is, the flux now is the integral over the entire surface of E dot d s. As I have said earlier, the electric flux is sometimes defined as the total number of lines of force of electric field crossing an area normal to them. Now, suppose we have a surface like this again, and there are two lines of force which are entering this surface and coming out. Then what happens? This elemental area d s here makes an obtuse angle with the electric field, because electric field is in this direction, the normal to the surface is in this direction, and this angle is more than 90 degrees. Similarly, here on this side these angles are acute angles. So, we say that the flux of these lines through the surface is E 1 dot d s 1 plus E 2 dot d s 2 plus E 3 dot d s 3 plus E 4 dot d s 4. Remember that some of these terms, as I have said, are negative, because this angle, cosine of this angle, obtuse angle, is a negative quantity, and therefore, the sum could be anything 0, positive or negative. If there are many more than the two lines of force going through a surface, then the net flux will be given by the integral phi e equal to integral E dot d s, where the integral is carried out over the whole surface. Let us take an example. Suppose we have a cube and the electric field is perpendicular to the surfaces 1 and 2. It is coming out through 2 and it is going in through 1. So, what happens? the same number of lines come through 2 as enter through 1. Therefore, the net flux through faces 1 and 2 is 0, and there is no flux through this face, this face, this face or the face opposite to it, because the electric field is parallel to these faces. Through face 1, the flux is E dot S, which is minus E S, because this angle is 180 degrees and cosine of 180 degrees is negative, and on this side the flux is E S or E dot S, and therefore, the sum of these two is 0. Take a sphere, let us say, then you can see from symmetry that as many lines enter this sphere, as many leave it, and therefore, the net flux through this sphere of this uniform electric field is 0. Having introduced flux, let us now study Gauss theorem, which is associated with the flux. The Gauss theorem states that the net flux out of a closed surface is equal to the total charge enclosed by the surface divided by epsilon 0, the permittivity of vacuum. In mathematical language, remember the flux is E dot d s carried out over the whole surface, and that is equal to q by epsilon 0, where q is the total charge enclosed inside the surface. Remember the word inside the surface. We are concerned only those charges which are inside the surface. Say for example, here we have 4 charges q 1, q 2, q 3 and q 4, but only 3 are inside this surface, and therefore, the Gauss theorem will take into account only these 3 charges q 1, q 2, q 3. It will not take into account q 4. Moreover, the shape of this surface or the size of this surface does not matter. Take another example. Suppose we take this surface. It has a charge minus 4 units inside and plus 4 units outside. As I said earlier, we will be concerned only with the charge inside this surface, which is minus 4 units, and not with the charge outside this surface. So, for the Gauss theorem, we are concerned only with the charge inside the surface. And why are we emphasizing so much Gauss theorem? Gauss theorem is particularly useful in getting the expression of the electric field, where charge distribution has some kind of symmetry. We shall see the examples of application of the Gauss theorem. First of all, let us prove the Gauss theorem, and we prove it for a single charge inside the surface. Then from the superposition principle, we will say that if instead of one charge there are many charges, then the theorem holds for all the charges inside the surface. So, we have this surface sigma shown in green color, and we surround this by what is known as a Gaussian surface, by a spherical surface which encloses this surface, the original surface. Now, by symmetry, this is a spherical symmetry. I mean, in a sphere, whatever way you look at it, in whatever way you rotate it, wherever you look at it, you see the same thing. That is known as spherical symmetry. So, because of symmetry, the electric field will only be radial to this Gaussian surface, and the area, if r is the radius of this Gaussian surface, then its area is 4 pi r squared, and the flux through it will be 4 pi r squared times E, the magnitude of the electric field, and the charge inside is q. Therefore, we have this equation 4 pi epsilon 0 r squared at a distance r from the charge, and the area is 4 pi r squared. Thus, the net flux through the spherical surface, and hence through the surface sigma, is E dot d s, the integral being carried out over the whole surface, which is equal to 4 pi r squared, because E is independent of the surface. So, therefore, we have 4 pi r squared into the integral of d s. So, q by 4 pi epsilon 0 r squared, and this becomes q by epsilon 0, which is the Gauss theorem. Let me remind you that what we have done, we have drawn a Gaussian surface. The electric field is normal to this Gaussian surface. Therefore, the flux according to Gauss theorem, E is E into 4 pi r squared, and that E is 1 by 4 pi epsilon 0 by r squared, area is 4 pi r squared. So, therefore, the flux is 4 pi r squared into E, and that is equal to q by epsilon 0, which is the statement of the Gauss theorem, that the flux through a closed surface is equal to the charge inside this surface divided by epsilon 0. Notice that the result is independent of the radius of the Gaussian surface. So, it can be any size. So, the Gaussian surface could be anywhere, it could as well be inside the surface, the sphere could be inside. All that is required is that all the lines of force must be associated with the Gaussian surface, those lines which are associated with the original surface. That is the condition. The proof given above could be true for each one of the charges inside the arbitrary surface. We have proved it one charge q, it could be true for q 1, q 2, q 3. Gauss theorem is a consequence of the inverse square law. We shall prove it in a moment, and will hold even if the charges were of one kind only. In fact, it holds for a gravitational field as well. You see, here we have two kinds of charges, there is forces of repulsion and attraction. In gravitational field, there is only force of attraction, and the Gauss theorem holds even for the gravitational field. So, since the electric field obeys the superposition principle, so E is E 1 plus E 2 plus E 3, integral of E dot d s is therefore integral of E 1 dot d s, E 2 dot d s, and so on, and that is equal to E 1 dot d s is q 1 by epsilon 0, E 2 dot d s is q 2 by epsilon 0, and so on, and q 1 plus q 2 plus q 3, they all add up and they give us the charge q. So, therefore, E dot d s, the integral of E dot d s is equal to q by epsilon 0, which is the Gauss theorem. So, if there are many charges, as long as they are inside the surface, then the Gauss theorem says that all the charges inside divided by epsilon 0, that is equal to the total flux through the surface. So, we have proved that Gauss theorem holds for any number of charges as long as they are inside the surface. In fact, if there is a continuous charge distribution inside a surface of volume V with volume charge density rho, then q is equal to rho times dV. If we take a small volume dV, then the charge inside it is rho dV, and if I integrate over the whole volume, then I get the total charge q, which is equal to rho times dV integral, where the integral is over the whole volume. And Gauss theorem then assumes the form that surface integral of E dot d s is equal to 1 by epsilon 0 times the volume integral of rho dV. In fact, in mathematics there is a theorem called Gauss theorem, which relates the surface integral to the volume integral. We have said Gauss theorem is because of the Coulomb's law, because of the fact that the forces vary as 1 by r squared, and now we shall prove it. We shall derive Coulomb's law from the Gauss theorem. For that purpose, we have a sphere once again of radius r, and we have a charge capital Q inside this surface, and we have a small charge q at this surface. And since the sphere is it has spherical symmetry, then there is a charge q at the center of the sphere, the field is radial to the sphere, and the flux through the sphere is 4 pi r squared, that is the surface area, times the magnitude of the electric field. So, that is the flux. Therefore, according to Gauss theorem, 4 pi r squared E, that is the flux, is equal to capital Q by epsilon 0. Capital Q is the charge inside the surface, giving the field at a point on the sphere as E equal to Q 4 pi epsilon 0 times r square. See, divide 4 pi r squared. So, this gives the field at the surface of the sphere. A charge q placed at that point, the field at this point is q by 4 pi epsilon 0 r squared, and there is a charge q. Therefore, the force on this charge is q by 4 pi epsilon 0 r squared into this small q, and you can see already this is in accordance with the Coulomb's law 1 by r squared. And the direction, since both the charges are positive, this is positive, this is positive, therefore, there will be force of repulsion, and therefore, the Coulomb's law says that the force of repulsion would be q q, by 4 pi epsilon 0 r squared. So, we have derived from Gauss theorem the Coulomb's law. It can be done the other way around also. In fact, as I said earlier, Gauss theorem is a consequence of the fact that force varies as 1 by r squared as mandated by Coulomb's law. Let us see a few applications of the Gauss theorem to fix the ideas. So, first of all, let me remind you that Gauss theorem is useful only if there is some symmetry, that the charge distribution has some symmetry. So, we shall take uniformly charged non-conducting solid sphere. So, the sphere, therefore, there is a symmetry and therefore, Gauss theorem can be applied. So, if the density of the charge inside the sphere is rho, then the total charge on the sphere is volume times rho, that is 4 pi by 3 a cubed rho. So, inside this uniformly charged non-conducting solid sphere, the total charge is q 4 pi by 3 a cubed rho. Now, the general procedure for finding the charge inside a sphere is to take a shell of radius r. I mean, I have told you already 4 pi by 3 r cubed, but let us prove it. So, what we do is we draw two shells of radius r and thickness dr. The surface area of the inner shell, let us say, is 4 pi r squared. The thickness of the shell is dr. Therefore, the volume is 4 pi r squared times dr. If rho is the charge density, then the charge in this shell is 4 pi r squared rho r dr, and the total charge therefore, is just the integral of that from 0 to a. And if rho is independent of r, it is a uniform charge density, then I can take rho outside, and the integral of r squared dr from 0 to a is simply r cubed by 3, and therefore, the charge inside is 4 pi by 3 a cubed rho. If rho r is a known function of r, its value is substituted in the integral this and integration is performed. So, this is a general method of finding the charge inside a uniformly charged sphere. Now, suppose we wish to find the field at a point P outside the sphere at a distance r from its center. From its center, we have a point P which is at a distance r from the center. This is the sphere which encloses charge q. We draw a spherical surface through P, Gaussian surface. Because it is spherically symmetric, the charge is all normal to it. Therefore, the flux is 4 pi r squared times the field. The flux is 4 pi r squared times the field, and that must be equal to the charge q by epsilon 0, charge q inside. What is the value of q? We have just derived 4 pi by 3 a cubed rho. So, we get E equal to a cubed rho by 3 epsilon 0 into 1 by r squared, and the field is directing outwards. So, in the direction of r cap. So, rewriting E equal to 4 pi a cubed by 3 rho divided by 4 pi epsilon 0 1 by r squared, we get the field at a point outside, which is equal to 1 by 4 pi epsilon 0 q by r squared. If you remember, that is the expression that you derived earlier for the field due to a charge q. So, this means that as far as the point outside the sphere is concerned, the sphere behaves as a point charge placed at the center of the sphere, because this distance r is from the center of the sphere. So, the sphere behaves as a point charge, and that point charge is placed at the center, and therefore, the field at point P is charged by 4 pi epsilon 0 times r squared. So, 1 by 4 pi epsilon 0 q by r squared. Now, let us find the field inside this uniformly charged non-conducting sphere. So, for this purpose, what do? We draw now a Gaussian surface inside. We had Gaussian surface outside. Now, we have a Gaussian surface inside, again of radius capital R. So, the charge inside this is 4 pi r squared into 4 pi by 3 r cubed, that is the volume of the sphere inside this Gaussian sphere, and the charge density is rho. Therefore, the total charge inside is 4 pi by 3 r cubed rho inside this Gaussian sphere, and if E is the field inside, it must be radial to the spherical surface, and therefore, the flux is 4 pi r squared times E, and this must be equal to q by epsilon 0 by Gauss theorem. So, we substitute the value of q and we get E equal to rho by 3 epsilon 0 times r. So, the field strength at any point inside the charged sphere is directly proportional to the distance r from the center. Distance r from the center, directly proportional to r. It is 0 at the center, and that goes on increasing with r. And at the surface, you can see, in fact, you can verify at the surface it is the same as the field for a point outside. So, at the surface the field is rho a by 3 epsilon 0. I make r equal to a, and this is what we derived earlier, the field outside from here. You see, if I make r equal to a, then I get the field at the surface, and it is a rho by 3 epsilon 0, and here also I get a rho by 3 epsilon 0. So, the whole thing is consistent. The field for the point outside, the sphere behaves as a point charge placed at the center. For inside, the field varies as the distance from the center. If you recall gravitational analogy, you will see that the value of g increases from the center proportional to the distance from the center. So, graphically we can show the situation. The field outside A varies as 1 by r squared, and inside it is 0 at the center and then keeps on increasing directly with r. E is proportional to r. At the surface, from both sides we get the field equal to rho a by 3 epsilon 0. So, there is a continuity, there is no discontinuity. In this lecture, we introduced first the idea of flux. I told you flux is something coming out of a surface. In this case, in the case of electric field, it is electric lines of force which are coming out of this surface. So, that is flux. And then we proved an important theorem called Gauss theorem, which says that if I have a surface and there is a charge q inside, then the flux through this surface, whatever the shape of the surface, whatever the size of the surface, the flux through this surface is equal to q by epsilon 0, and to get the flux we have to integrate over the surface. In the next lecture, we will continue with this study of Gauss theorem.